Today we are going to start a new chapter which is electromagnetic waves, in short EMW. Now before starting that, we will see some conclusions from the previous lectures, that is from the previous chapters. Now in moving charges and magnetism, I have told you that current creates magnetic field, or moving charges create magnetic field. Now when the charges are at rest, that will only create electric field. Now when the charges are moving, then that will also create magnetic field around it. Okay. Now moving charges create current, and for current we need a conductor. Why? Charge is always carried by material or particles. Now whenever there is a material for the movement of charges, that is conductor, then only charges can move. So if there is current conductor, then only current is possible. Now if there is current, then only magnetic field is possible. Now let me ask you a very interesting question. Whenever there is a moving charge, for example, not moving charge, whenever there is a battery connected to a conductor, will there be electric field in it? See, when charges are at rest, it will give electric field around it, right? Electric field will not be around it, electric field will be away from it in the case of positive charge, or towards it in the case of negative charge. Now whenever current is moving around that, we will be having magnetic field, verbally if I am saying in this way. Okay, now whenever we are taking a conductor, let's say it has got 10 electrons. These are free electrons, or these electrons can move across the conductor. Does that mean that there is a net charge of 10 electrons? No, because these free electrons were basically part of certain atoms before, correct? As it got energy, now from the same atom, from one atom, it has moved to the void, or this electron become free. See, the net charge still that is equal to 0. For example, let's say I have 4 proton and certain neutron. Anyway, neutron I am not considering. Now in the 2 orbits, I have 2 electron in the first orbit and 2 electron in the next orbit. Now this material, this electron, whenever it is getting sufficient thermal energy, that will move from here to voids, or now this electron will become free. This electron will be there inside the conductor itself. Now what is the net charge initially? When the electron was there, 4 electron, 4 negative and 4 proton, 4 positive, net charge was 0. Now when the electron is taken from this atom to outside, now the whole thing contribute the conductor, right? So inside the conductor we have positive charged atoms, and at the same time electrons are there, free electrons are there, so that net charge will be 0. So whatever the amount of positive charge we have, to the same amount we are having negative charges. So for example, I have 5 positive and 5 negative. Now whenever current is going, for example, one electron is entering at one end. Now what will happen? At the same time, one electron will leave other side. This is series connected, right? So whatever the rate of movement of charges here, it will be same. So if 5, see what is current? I is equal to Q by T. Now in 1 second, if 2 electrons are moving here, then at the same time, through every point, 2 electron will be the movement, because current have to be same. These are connected in series, right? So there is no additional charges given to a conductor when current is going. So when there is no additional charge, what will be the net electric field? 0, because number of positive and number of negative is 0. No net charge, only charges can make electric field. But this can, as there is movement of charges here, individual charges, there will be magnetic field around it. Okay, so if this is the current carrying conductor, around it we will have magnetic field. Now Maxwell has done an experiment. There was a current carrying conductor, so I will make it DC. A cell is given. So initially the capacitor is not charged. Now let's say I have a switch here. The moment I close the switch, what will happen? Charges will start accumulating here. Positive, 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 and negative, 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 negative. So initially I can say that one after other it will be going. So whenever one positive is added here, at the same time one negative will be induced by the positive charge. So there will be an electric field created in this way. Now one more positive will come and one negative, electric field created in this way. One more positive will come, one negative, electric field created in this way. One more positive. So similarly, till this become fully charged, this process will happen. Now one thing is for sure here, there is change in electric field. Initially it is 1, then 2, then 3, then 4, then 5. It keeps on going till where? Till the capacitor is fully charged. So initially Q is equal to 0. From there till Q is equal to Q till the capacitor is charged fully, then electric field across these plates will be increasing. So that is the only change here. As of now, I am going to ignore these field lines. So you understood that that will be the change, right? Okay. Now whenever the charges are getting accumulated, we know that there is certain current here. Okay. So because charges are moving here. So Maxwell has kept a magnetic needle here and he has seen a deflection. And what is the reason for the deflection? Because the charges have came here. Okay. So there is a current here. So he got a deflection in the magnetic field. So as per Ampere's circuital theorem, B dot dl is equal to mu 0 I. So when I is there, magnetic field will be there. So here, whenever the capacitor was charging, there was charges moving here. So we can see a magnetic field here. So that magnetic field will give a deflection to the needle. Now at the same time, after this experiment, he kept his magnetic needle here and observed. So what we are actually expecting, there shouldn't be any deflection, because when I am considering an Amperian loop here, is there any current passing through the Amperian loop? No. Here there was, because we have a conductor here, it will be sending the charges. But here in this case, at this case, current is equal to 0, the whole thing will become 0, but dot dl, see, length will never be 0, which means magnetic field is 0. I'll repeat it. Current is 0. So this whole thing will become 0. And total length of my loop is not equal to 0. So a number multiplied by non-zero value, if it is 0, then number is 0. For example, 2 multiplied by a value is equal to 0. So the one number x multiplied by 2 is equal to 0, which means x is equal to 0. Similarly, b is equal to 0 at this point. But then how did we got a deflection here? So this was Maxwell's question. But this has proven right. Actually, this Ampere's circuital theorem was absolutely right. He has proven it. We were applying Ampere's circuital theorem. Maxwell has told that this one is right, because here this can be applied. But this is not sufficient. This cannot be applied anywhere. We need certain additional terms so that this can be considered at all the cases. Then Maxwell has told that whenever charges are getting accumulated here, see, electric field keep on increasing. Now this change in electric field is basically bringing a current here. Okay, now this is the equation. This is the equation for Ampere's circuital theorem. Maxwell simply have came and given an additional term here, that is mu 0 into ID. He told that whenever there is a conduction current, we can use it. This is called as displacement current. See, in between plates, basically there is current, but it's not due to movement of charges. What is the reason? The change in electric field is making a current. See, be very clear with that, there are no movement of charges. So we can't call this as conduction current. See, this current he was able to observe when there is a change in electric field. So the change in electric field has created a quantity which is similar to current, and he has mentioned this as ID. So this is ID. Now the equation will become mu 0 into I conduction plus ID. So dID means displacement current, IC means conduction current. Now what is the value of ID? ID is equal to, we know that the reason for ID is change in electric field. What is that? dE by dt. The reason is this one. So I can say that higher the change in electric field with respect to time, higher will be the displacement current. Now with experiment he has proven that not only electric field, reason is change in electric field, but the value of ID dependent on area as well. So he has got an equation that ID is directly proportional to dE by dt into area. Now what is E into area? Electric field into area is equal to electric flux. So ID is directly proportional to d by dt of phi E. This is very important. Phi E is electric flux, E into A is phi E. That is the that is the substitution we have made. Okay. Now this is a relation. So how can we convert it into equation? By multiplying with constant of proportionality. So ID is equal to constant of proportionality here is epsilon 0. So epsilon 0 into d phi E by dt. This is very important. Now obviously area will be constant in this example. See, as per this experiment area will be constant. Now the area will not change. So phi E you can open here. Phi E will be electric field at that point into area. So area as it is constant, you can take it here. So this is the best equation that gives the value of displacement current. Displacement current is equal to epsilon 0, that is permittivity into area into time rate of change of electric field. Now I am going to substitute it here. So mu 0 into IC is conduction current, ID is this one, epsilon 0 A dE by dt. Multiply it across. So that will be mu 0 IC plus mu 0 into epsilon 0 into A dE by dt. This is BDL. Now the equation has now got modified into a new value. See, till here amperes has given, right? Integral BDL is equal to mu 0 into IC. This is Ampere's circuital theorem. But this contribution was made by Maxwell. So this is, after this introduction, the whole equation has been named after both the scientists. So that is Ampere's Maxwell equation. Okay, so this one is Ampere's Maxwell equation. You can also name it as Maxwell Ampere's equation. Okay, so we have Ampere's component element here and Maxwell element here. The total is making the equation. This is the foundation for this chapter. Very important. Okay, thank you.